you can carry out your reaction in basic conditions and in acidic conditions, and you have different mechanisms in this case. Now, first of all, about basic conditions. Of course, this mechanism is the same for aldehydes and for ketones because of the place the group which we are interested for is our carbonyl group. Now, first of all, if you have basic conditions, so the first step is action of your nucleophile on carbonyl group's carbon. Because of here carbonyl group's carbon has positive charge. And alkoxide ion is formed. This alkoxide ion. As you see here, you have that animal double bond, and you have nucleophile here. After that, acids or waters, H protein, X2 carbonyl group's oxygen, and you get OH group here, and finally anion is separate, and of course this anion finds something which has positive charge, and finally you get proton. This is in acidic conditions. Now let's look what you have in basic.
No, in acid.
Oh, sorry, acidic. This was a basic.
Yes.
Now what we have in acidic conditions. In acidic conditions, first of all, your acid or water protonates your carbonyl group's oxygen. What means protonates? So here this bond breaks and H goes to carbonyl group's oxygen, and you get protonated carbonyl group. After that, nucleophile X on the carbonyl group's carbon and forms this transition complex. After that, anion X on the nucleophile's H breaks this bond, and finally you get once again the same product, and HA is acid or water, so this one is solid. Now what's itself about reactions? I give you directly not mechanism is what this one in acidic conditions and in basic conditions. How you can write these reactions with some nucleophiles or neutral molecules. So reactions of aldehydes and ketones. And I show you only way how you can write product of these reactions. But this is not mechanism of this reaction. So first of all, let's discuss about reactions where your carbonyl group converts into COH group. So any aldehyde, any ketone gives product which looks like this. Any aldehyde, any ketone. It doesn't matter which one you have. Class. If you have water, so something in which you have H, but not in all cases. H goes to carbonyl group's oxygen, OH goes to carbonyl group's carbon. Once again, this one isn't mechanism of this reaction. This is way how you can draw the product structure. So you get RCOH, HOH. The name of this product is hydride or gel. Next one, aldehyde plus alcohol. Any alcohol, which one you want? HO, for example, R, right? So if you have different radicals. Once again, H goes to carbonyl group's oxygen, O goes to carbonyl group's carbon. So you get R, C, O, H, O, R. The name of this product is acetone. Acetone. Now, next reaction. Hemiacetone. Yes. Hemiacetone. Or hemiketone. If you take ketone, so you get hemiketone. If you take aldehyde, so you get hemiacetone. So it doesn't matter. Maybe I use hemiacetone for aldehydes and ketones. Both. oxygen NH2 goes to carbonyl groups carbon. And you get RCOH, H, and H2. This product's name is cyanohydride. So, as you see, cyano NH2, yeah. RCOH, H and NH2. So once again, as you see in all these reactions, your carbonyl group converts into COH. Of course, all these reactions can go in acidic conditions or in basic conditions, but in any case, your product will be hemiacetal, cyanohydrin, gendiol. So you have acidic conditions or basic conditions, it doesn't matter which one you have. And now let's discuss about this scheme. As you see here, you have two versions. If your nucleophile attacks carbonyl groups carbon, first of all, you get this transition. Guys, go out. You do, quickly. Quickly. I'm waiting, quickly. If somebody wants to talk, go on. As I see from this cartoonish group, 1, 2.
No, they're all
Now look, in this case, in first version, carbonyl group's carbon is attacked by nucleophile. You get this transition and this transition state complex, and after that, after addition of solvents H proton, finally you get this. So all of these reactions according to this mechanism. All these reactions. Now what about second version? Second type of reaction. This is reactions with amines, primarily amines, with hydroxylamine, with hydrazine, with aryl hydrazine. This reaction looks as product looks as you have a substitution reaction, but really this is nucleophilic addition reaction. Now look, if your nucleophile with its H atoms, once again here your nucleophile, your nitrogen need 2 H atoms. So your nucleophile attacks this carbon atom, you get first of all this transition state. After that, 1 H atom as proton goes to carbonyl groups oxygen, protonates this oxygen, and on this middle state you get like this alcohol. But after that, water molecule removes, so these OHs, this H take each other and give H2O, and you get product where your nucleophile is bonded with carbonyl groups carbon by double bond. So looks like substitution. So like your oxygen substitutes by nucleophile, but really this is addition-elimination reaction. First of all, after addition you get this product, this alcohol, and then elimination of water, removing of water, finally is your final product. Now, what about these reactions? carbonyl groups oxygen and NH2 carbonyl group carbon. In this case, you have absolutely another situation. You have addition, elimination, reaction. Now let's start. For example, if you have some aldehyde, CH3COR, and once again, it doesn't matter you have aldehyde or ketone. You have the same situations, the same structure product. So, plus, first of all, let's discuss from amine. So, primary amine looks H2, and for example, if you have here CH3, once again, you have which radical, it's not very important, which one? So, once again, take like this, and this goes here. Once again, I show you only way how you can write these reactions. Really, its mechanism looks like this. So, finally, you get CH3C double bond and this CH3. And here you have once again H. And your another product is H2O. In first four reactions, you have another product, inorganic product. You have only organic product, gel or cyanohydrate. Here you have water molecule. Why? Because of this one is addition, elimination, reaction. Now the name of this is amine. So it's general name, amine. From amine you get imine. This first reaction. Now second one. Once again, you have some aldehyde or some ketone plus hydrazine. H2N and H2. Once again, take these oxygens and two H atoms from hydrazine molecule. This part goes here. So you get CH3C double bond and H2, H plus H2. The name of this one is hydrazine. Hydrazine. The name of product is hydrazone. Hydrazone. So from hydrazine you get hydrazone. Now next reaction is reaction with aryl hydrazine. So what means aryl hydrazine? If instead one H atom you write benzene phenyl rings radical C6H5, so you get aryl hydrazine. Now CH3C double bond OH plus H2N and H, and here you have C6H5. This one is aryl hydrazine. So once again, take oxygen and two H atoms, and you get structure of your product. C double bond N and H. C6H5 H plus H2O. So this product is aryl hydrazone. Aryl hydrazone. Now, as you see, all these reactions, really your reaction mechanism looks like this. First of all, you have addition steps, product, and after removing water molecule, finally you get this structure where your nucleophile is bonded with carbon atom with a double Oxygen. So, as you see, these two versions are not same. This is only way how you can draw product structure. Only this. But this one does not correspond to the reaction mechanism. This is your reaction mechanism. You understand? There are differences between them. So, now what about reactivity of aldehydes and ketones? Because of in both molecules, in both classes, your center reaction, reacting center is carbonyl group. So if your carbonyl group is bonded only with one radical, so in this case, you have aldehyde. Always aldehyde is stronger and better as electrophile than ketone. Now why? I told you that in carbonyl compounds, in aldehydes and ketones, your carbonyl group is polarized group. Here you have very polar covalent bond. C double bond O. And oxygen attracts these electron pairs which are in the bond, and it has positively, partially negative, and carbon has partially positive charge. Now, nucleophile always attacks your carbonyl group's carbon. Why? Because of here you have the more positive charge. And this one is your electrophile. Nucleophile always attacks electrophile. Now, if here you have some radical, aliphatic, I am talking about aliphatic aldehydes and ketones. If here you have some radical, for example CH3, and second one is H, so this one is aldehyde, yeah? CH3 group has positive inductive effect, and this one is electronegating group. So it gives electron density to this carbonyl group's carbon. So what it makes? It decreases the positive charge of your carbonyl group. In any case. Now, if you have two radicals, in this case, two radicals decrease more than one radical of this positive charge. That's why aldehydes are more reactive than ketones. If we are discussing about aliphatic aldehydes and ketones. So, if you have benzaldehyde, this one, in case of benzaldehyde, phenylradical has positive mesomeric effect, so it gives these electrons, and once again, here we have conjunction between this double bond and this aromatic ring double bond, and finally your carbon's positive charge once again decreases. So aryl aldehydes are less reactive than aliphatic aldehydes. Why? Because of here you have action of your now, this is your aldehyde. As you see, it has plus mesomeric effect. It donates resonance structures electrons, and as you see, these two electrons go here. So you have here double bond. These two electrons flow to the oxygen, and your oxygen has around 6 electrons, you see? And here you get positive charge. After that, these two electrons. This, do you remember this mesomeric effect section? When you have pi system and neighbor, you have next to positive charge. So in this case, these two electrons are consist of 2 electrons and with this pi bond. And this one has minus mesomeric effect, and this has plus mesomeric effect. Once again, if here your double bond move, so you get positive charge with this carbon. Once again, now these two electrons act on this positive charge, and your double bond moves here. You have here and here, and here you have double bond. So as you see, you have conjugated system, and your carbonyl group's positive charge travels around this aromatic ring. And what it means, it decreases your aldehyde's activity. That's why aliphatic aldehydes always more reactive than aromatic aldehydes. In case of aldehydes and ketones, aldehydes are aliphatic aldehydes and ketones. Aldehydes are more reactive than ketones. Why? Because of here you have methyl, some alkyl groups which have electron donating properties. Now what about formaldehyde? In case of, and remember please, if we discuss about the formation of gem dyes, it's a reaction with water molecule, yeah? Only in case of formaldehydes, your equilibrium shifts to the right side. Why? Because of here instead H atom you have, instead the radical you have H atom. And formaldehyde hydrates, really you have irreversible reaction, really in this case. Now here once again is addition of water molecule. So in basic conditions what you have, and in acidic conditions what you have. Once again, if you have basic condition, first of all, your nucleophile attacks carbonyl groups carbon. First of all, outside ion is formed. It's middle step. After that, your solvent molecule, water or acid, protonates your these carbonyl groups oxygen, and finally you get gel as product. This is in basic conditions. In basic conditions, do you remember first of all carbonyl groups oxygen protonates by solvent molecule. In this case, water goes as solvent and as a reactant too. And first of all, you get this protonated product. After that, another water molecule, as nucleophile, attacks your carbonyl group's carbon, and after that you get this intermediate product, and then by removing of water molecule, you get finally your gel as product. So once again, you can carry out this reaction in basic conditions and in acidic conditions too. Come down. You need only this part. You know this from amine, you get imine. This is imine. Not this part, not the amine. Only this part. So here once again, gel formation, base catalyzed reaction. So once again, if you have base catalyzed reaction, first of all, your nucleophile attacks your carbonyl group's carbon, and then your solvents from solvent molecule, H1 proton goes to carbonyl group's oxygen, and finally, after removing an ion, you get your product. In case of acid catalyzed reaction, first step is protonation of carbonyl group's oxygen. After formation of intermediate gel, and after that, removing of your catalyst. Now once again, carbonyl group, protonation, first step. So you get this proton. After that, action of second water molecule, for example, second nucleophile, and you get this intermediate transition state product, and then water molecule removes like H3O, and finally you get hydrate or gem dye. Now, this reaction is once again in case of reaction with alcohol. First of all, you need here acid as catalyst. Why? Because of its alcohol's molecule is weak nucleophile. And if you use acid as catalyst, so it activates your carbonyl group's carbon. This carbon, in this case, has more negative, more positive charge. So, first of all, once again, protonation, then action of alkoxide ion, formation of this transition state, after that removing water molecule, and finally you get acetal. So, if you take only one alcohol molecule, you get here hemiacetal. But if you use two molecules of alcohols from hemiacetal, you get acetal. I mean only hemiacetal state, not acetal state. But in any case, I can write these reactions equation 2. Now look, if you have CH3, C double bond OH plus HO, C2H5, for example. So H goes here, O, CH3 goes here. First of all, you get hemiacetal, yeah? CH3, C, O, H, H, O, C2H5. But if you use a second molecule of alcohol, so HO, C2H5. Now look, this part goes here, yeah. And you get, oh, sorry, without this. CH3, CO, C2H5, HO, C2H5, plus H2O. This is hemiacetal, this one is acetal. Hemiacetal and acetal. From ketone you get hemiketal and ketone. This acetal formation, now once again, alcohol and aldehyde always gives hemiacetal, alcohol and ketone gives hemiketal. So the mechanism in both cases are the same. Oh, I forgot cyanohydrin. I give you. So once again, if you have aldehyde and if you have HCl, it's hydrogen cyanide itself. This one is acid. Now, which reactions need catalyst and which reactions don't need catalyst? If you see HCl, guys.
Children.
If you see HCl itself, HCl is acid, yeah? So it can catalyze itself, its reaction. So here you don't need catalyst. You need catalyst with water, with alcohol, but with amines. You don't need catalyst if you have reaction with hydrazine or hydrazine or oxime. In this case, without catalyst, this reaction takes place. Now, in the case of cyanohydrin, once again, look, H goes to carbonyl group's oxygen, CN goes to carbonyl group's carbon, and finally you get cyanohydrin. Cyanohydrin. Now, mechanism of this reaction. First of all, your nucleophile is cyanide.